It's time to get our hands dirty, or at least our mouse clicking fingers. Welcome to this video on Azure Machine Learning. My name is Kevin Fiesel. I am the proprietor of Catalxy Services LLC, a consulting firm which specializes in work all across the data platform space, especially SQL Server. In the prior video, we used Azure Machine Learning's automated ML capabilities to train 1,000 models against a dataset, choosing the best result. This video will be a bit different. Instead of mass training hundreds or thousands of models, we're just going to create one, and to do this, we'll use the Azure Machine Learning Designer. The Azure ML Designer is a drag-and-drop interface for Azure ML. If you're familiar with tools like SQL Server Integration Services, Informatica, or Apache NiFi, this style of interface will make intuitive sense to you. We're going to see a bit about how the designer works, so instead of me talking to you about it, let's jump right into a demo. We are in Azure Machine Learning Studio, in my CS Azure ML workspace. By the end of this demo, I'm going to show you how to build a training pipeline for a machine learning problem. By navigating to pipelines and then choosing the Chicago parking tickets fixed model pipeline, we can see the end result. There are several components which make up this training pipeline, and as I scroll through them, we can see a flow from raw data to a trained model and finally scored data. I can do all of this with a drag and drop interface and limited knowledge of data science or machine learning. So let's create something like this ourselves. The first thing I will do is navigate to the Compute tab and check out my list of compute instances. We can see that I have already turned on my CS Compute instance, so I will not have to wait for it to start up. We'll perform our model training on a compute instance because we don't need to do an enormous amount of processing, and so we don't need to wait for a compute cluster to spin up. If you do not have a compute instance, we can select the New option to create one. I recommend creating one of size standard DS12 v2 or higher, which is 37 cents per hour USD. The smaller compute instances are less expensive, but you might struggle to work with certain algorithms which tend to be more memory hungry. I don't need a new compute instance, so I'll select Cancel to return to the prior screen. Now that I know my compute instance is powered on, I will navigate to the Designer tab. This is where I can create new pipelines. Note that there are some sample pipelines for performing tasks like image classification, binary classification, recommendation, and so on. If you are brand new to the idea of machine learning, you can use these to get started and understand how components fit together in the designer model. Instead, I'm going to choose the option to create a new pipeline. This takes me to a canvas as well as a flyout pane which contains data and component tabs. I'll choose the data tab and then drag my Chicago parking tickets dataset onto the canvas. By doing that, we can see a component on the canvas which emits a data output. If I hover my mouse over the circle, we see that the output is an ML table. Azure ML's designer works through a series of interface contracts. Components expect certain types of inputs and emit certain types of outputs. It's our job to hook up the steps along the way, but the designer will let us know if we are trying to do something we can't. The next thing I'd like to do is switch over to the Component tab. There are dozens of components, and navigating through them can be time-consuming, so I like to use the search box. I'll type in the phrase clean missing data and hit enter. That shows me two result sets, one dataset and one component. Let's drag the component onto the canvas. Note that it takes in a dataset and emits a cleaned dataset and the cleaning transformation. The input dataset is of type data frame directory, which is compatible with ML table. But the component still has a red error message, and if I hover over it, I can see that a value is required. By double-clicking the component, I can see the problem. We don't have any columns listed to be cleaned. In the prior video, we learned that AutoML found 4 columns with missing data. I'm going to fix the 2 numeric columns, tract, and police district. To do this, I'll choose Edit Column and enter Tract, and then choose the right column. I'll repeat this with police_district, and then choose Save. I also want to change the cleaning mode from custom substitution value to replace with mean. As we can see, that changed the subsequent questions we need to answer on this form. I'm okay with the defaults on this component otherwise, but if I wanted to change something like which compute target the component runs against or the name which shows up in the graph, I could do so here. Let's hide that flyout panel and move on to the next step. The next step for me is to add a component to split the data. Once again, I'll avail myself of the search box and then drag on a split data component. This takes in a dataset and emits two subsets of the data. If I try to drag on an invalid input, like this cleaning transformation output, I cannot make the connection. This is a built-in capacity to lessen the risk of doing something catastrophically wrong. Instead, I'll hook up my cleaned dataset component and then double-click the split data component. The flyout panel now shows me the properties of this component. The kind of split I want to do is a simple train test split where I'll train with 70% of the data and retain 30%. To do this, I'll change the fraction of rows in the first output dataset to 0.7. I want this to be a randomized split, and for the sake of consistency from demo to demo, I'll use random seed 19008. We could also choose to stratify by some column, meaning ensure that unique values in this column show up in both the training and test datasets. This is important in cases where we have one categorical column with some rarely selected values, and I want to make sure that we have cases in the training dataset so that we don't blow up if the test set includes them. I don't need to do that for this dataset, so instead I'll hide the panel. At this point, I need to select an algorithm to train this model. To do so, let me first clear out the search menu so that all of my components are visible again. Now I'm going to navigate into machine learning algorithms. There are 19 algorithms in total, but because I know I'm working with a classification problem, I can scroll down to the classification options. Even so, I still have 12 of them. My dataset has a binary label. As we know from the prior video, we're asking the question, does this person still owe money to the city of Chicago for an unpaid citation? For that reason, I can skip the multi-class options and stick with two-class options. I'll choose the two-class decision forest, a very common algorithm in the data science and machine learning world. When I drag this component onto the canvas, we can see that it has no inputs and one output, an untrained model. So how do we hook this up with our datasets? Well, the way that we do this is with a train model component, which I can find in the model training section. Dragging one of those onto the canvas, we now have an input for an untrained model, as well as an input for a dataset. Let's wire these up, making sure we use the leftmost output from the split data component, as that has our 70% for training data. Double-clicking on the decision forest component, I have a few options I can choose, or hyperparameters. There's no perfect advice on which hyperparameters you should choose for a given model. That's something you'll have to discover by reading literature about your specific problem or trying out various options to see what works best. For the sake of trying something out, I'll set the number of decision trees to 32 and the minimum number of samples per leaf node to 8. This decision forest will use a resampling technique known as bagging, or boosted aggregation. The short version of this is, we'll try out a large number of moderately effective decision trees and have the trees vote on an answer. The algorithm itself handles voting and, based on how that voting goes, gives us back a final answer for our label. To make the voting more interesting, the algorithm does things to the trees like limiting the subset of data they get to see, or limiting the number of features they get to use. That way, we end up with different trees holding different perspectives of our data. Let's close that panel and then double click on the Train Model component. Here is where we set our label. To do so, I'll select Edit Column. In the column name box, I'll enter Payment is Outstanding and strike Enter. Because I performed a data cleanup earlier, I won't get auto-completion of column names, so I have to make sure everything's spelled correctly. I did check that, so let's choose Save. Then, I'll turn on Model Explanation, as it could be interesting if we want to understand how this particular model came to its conclusions. After closing the panel, let's add a Score Model component. I'll search for that and drag it onto the canvas. This allows us to see how our model performed when running against data it has not already seen. We'll wire up the score model using our trained model and scoring dataset. This generates a scored dataset output. The final thing I want to add is an evaluate model component, which takes our scored dataset and builds high-level summary metrics from it. Before I can run this pipeline, I need to do one more thing. Let me select the Settings button. I need to choose my compute type, which I'll set as my active compute instance. Scrolling down to the bottom, I can also name this pipeline, so I'll choose Chicago Demo Video as the pipeline name. Finally, I want to make sure everything is fine, so I'll choose Validate. The designer indicated that we have no problems, so I can submit the pipeline. From there, I can choose whether to use an existing experiment or create a new one. I'll create a new experiment, which I can call Chicago Demo Video. From there, we'll kick off the job. This shows us a Submitted Jobs pane. Selecting the job detail link takes us to a view where we can monitor the progress of our job. Now, this is going to take a little bit of time to complete, so let's just skip ahead until we're done. Editor, if you please. Now that our job has completed, we can analyze the results. There are two areas I'd like to analyze in particular. The first is in Score Model. I'll right-click on the Score Model component and then choose Preview Data and then Scored Dataset. I can look at data for each of the 21 columns in this scored dataset. At the top, we have the distribution of results. So if I choose the hardship index column, we can see a fairly heavy skew toward lower numbers. And because this is a numeric feature, I get a larger histogram in the panel on the right-hand side. Scrolling further along, I see my actual label, which is Payment is Outstanding. After that, I have the scored label, which is Azure ML's prediction of what that value would be. I also have the actual probability of payment is outstanding equal 1, so we can see just how certain the model was that this person would skip payment. Finally, let's hide this flyout panel and evaluate the model. To do so, we'll right-click on Evaluate Model and then select Preview Data and then Evaluation Results. This gives us a few ways to view our classification problem. At the top, we have 3 curves. If I scroll down a little bit, we can see on the left-hand side a series of metrics indicating how the model did. This particular model did reasonably well in accuracy and precision, but poorly in recall. To understand how these measures come about, we have a confusion matrix on the right. The recall of 0.184 comes from the question, given that a person did in fact skip out on paying their parking citation, what is the likelihood that we indicate the person would do so? We got 15,299 right out of a total of 83,158, or 18.4%. One nice thing about the way we see these results is that I can move the threshold slider, which changes how we make true versus false predictions. If I set a threshold to something like 0.28, that says anything with a prediction of 0.28 or higher will be marked as true, and 0.27 to 0 would be false. At the value 0.28, we maximize our F1 score at 0.545. And we do a pretty decent job on recall, though our accuracy has dropped and precision has become bad. Deciding where to set our threshold is a problem for another day, however. There's quite a bit that we did in this video. We learned how to train a machine learning model using the Azure ML Designer, score that model, and evaluate its results. We've only touched on the functionality available, but hopefully this whets your appetite for more. In the next video, we're going to convert this training pipeline into something other applications can integrate with. We'll have links and show notes in the description below. And until we see each other in the next video, take care.